This is a talk about calendrical C++. It's, I hope, an entertaining and informative talk. It is a talk that was sort of subbed in because of a cancellation. I anticipated, when I pitched this talk, I said, you know, are you tired in the middle of the C++, now weak? Is your brain full of too much high-powered C++? Come to this talk for a bit of a relaxation and more like real-world problems and no template metaprogramming. So if you want to leave now and see a real C++ talk by Zach or Sean, that's fine. I won't be offended. There is plenty of C++ in the talk. I feel like I have to give a disclaimer on every talk now that I didn't use any AI in the preparation of this talk. So any mistakes you see are mine. If you enjoy this talk, go see Cassio's talk, which is more calendar geekery. If you don't like this talk, go see Cassio's talk because it might be better. And let's get into it. So I'm interested in lots of things. But for today, I'm interested especially in time and calendars. I've spent a year geeking out on this stuff. I should also, my employer would like me to tell you that I'm now employed by Intel as a principal engineer. I almost never do an about me slide, but I work in the chipsets group, and I specifically work on power management. So the bit of the chip inside the package that controls the power to all the other parts of the chip. And it may surprise you to learn that in that very constrained embedded environment, we're using C++20. And it's great. Anyway, that said, this is about time and calendars. I'm also interested in heraldry. I'll bend your ear about that if you find me. The genesis of this was really back at the very beginning of my career. I was working in games. I was playing a game called NetHack, which is one of the original roguelike games. And NetHack has all this richness of interaction in it. And one of the things it has is a phase of the moon calculation inside the game. So if you're playing, it's an RPG, and if you're playing it during a full moon, it adds points to your luck. Or conversely, during a new moon, you become quite unlucky. And I had a phase of the moon widget in my system tray in Windows 95. And I was friends with the lead programmer on the game Dungeon Keeper at the time. And I had a copy of Numerical Recipes in C. And in Numerical Recipes in C, one of the first sort of bits of code is, and I hope you can all read this. This is a much bigger room than I'd really like. This wall of text appears, and it's called FL Moon, full moon. It's C, because it's Numerical Recipes in C. And this ostensibly calculates the phase of the moon. So this is a routine. It takes two inputs, N and NPH, which mean the nth moon and the nth phase, where the phases are 0 for new, 1 for first quarter, 2 for full, 3 for last quarter. And the return value is actually in the in the pointers to floats that we give it, because this is a C routine, right? And it returns the Julian day and the fractional part of the Julian day. The Julian day the Julian day number is a count of days since November the 24th, 4714 BCE. And there are 7,980 days in a Julian day period. Anyway, there's literally a comment in the book that says, you're not expected to understand this, but it does work. And as you can see, it's full of magic numbers. So anyway, I had this, and I went to Simon Carter, and I said, you've got to put something in Dungeon Keeper based on the phase of the moon. He said, I'm far too busy. Send me the code, and I'll put it in. So I did, and the result is that if you play Dungeon Keeper, which is now a very old game, I don't expect anyone to have heard of it. When the full moon is outside your actual window, you're able to play one of the secret levels. It's triggered off that. So that was kind of where my love affair with this kind of thing started. All right, let's briefly talk a bit about time, and time as it exists in C++ today. If you haven't seen this YouTube talk, I highly recommend it at your earliest convenience. It's 10 minutes about just how painful it is to implement time and time zones. So of course, C++ gives us the Chrono since C++ 11. One of the basic types is a duration, and C++ 11 and now some extra stuff in 20, we get a bunch of different durations. We get nanoseconds all the way through to hours, and then in 20 we also get days, weeks, months, years. And they are just a representation and a ratio, the ratio representing seconds. So we get durations. We also get time points. So time points and durations form two types that form a affine space, a one-dimensional affine space. And we get all of the ways to add, subtract, arithmetically bring them together, calculate with them. So a couple of things I want to say about using Chrono. There's a couple of tips I've learned about using Chrono. It's great because it can be applied piecemeal to a code base, first of all, and you don't have to convert the whole thing to using Chrono. Conversions can happen at interface boundaries or I/O boundaries. That's very typical. And when you use Chrono, any kind of conversion which entails no information loss is usually implicit. So you can implicitly convert seconds to microseconds because there's no information loss there. But you can't go the other way around. That's when you need a specific cast, a duration cast. And using Chrono just eliminates whole classes of bugs. Like, when you go from using integral types as time, you have bugs like, oh, I accidentally passed seconds to this function expecting milliseconds, or the other way around, and now I'm wondering why my program just froze at that point, because it was waiting for 3,000 seconds to pass by, right? This doesn't happen if you start using Chrono. And one of the tips I have for Chrono is, as humans, we tend to think of time in the units we learn when we grow up. So we think of time happening in seconds, or happening in milliseconds, or happening in microseconds. Defining your own durations and clocks in Chrono is really easy, and it's a good thing to do. And if you can sort of break your mind out of thinking about things in milliseconds or microseconds and thinking about them in the actual sort of native periods that they need, then Chrono is just as easy to use that way, right? There's nothing special about the number 1,000, except it's the cube of number of fingers I have, right? So yes, one of the things you can do in Chrono is make your own clocks. This is what you need to do in order to make your own clock. It's basically some type defs and one function called now, and then you are a clock. So you need a representation type, which is something integral, probably. A period, which is the ratio, right? So 1 is seconds. And then duration and time point are derived from those. And then you have a way to get the now, like what instant of time it is now. So, example of doing this. I've done this. I was a game programmer for many years. I wrote network games. And it's important for the server and the client to agree on what the time is. So when the client connects to the server, that basically means synchronizing a clock, and the server can make a clock, and the client can make a clock. Each one can make a clock representing the other end of the connection. And synchronization is just setting the epoch of each clock respectively. So when the client connects to the server, there's a handshake and a bit of back and forth to determine how we agree on the time. But having done that, the client can have a clock that represents server time, and so it can tell when everything is happening with respect to the server. So making a clock is good for that. This is what I say when I mean stop thinking in terms of milli or microseconds. This is probably the most common, I don't want to exactly say error, but the most common kind of use of Chrono that isn't as good as it could be. Because as humans, we think in terms of microseconds, milliseconds, whatever. But if I have a real-time clock crystal that's ticking at 32.768 kilohertz, very commonly I see this code, right? It's converting it to milliseconds whenever I ask for now or ask for the ticks. Instead of doing that, why not just create a duration that is the time period of the clock? Everything, all that conversion will happen inside Chrono only when it's needed, and only safely, right? And oftentimes at compile time if it can. So that's probably my number one tip for using Chrono is make your own durations that represent the native type, the native period of what you're doing. Here's another example of where I did that. This is, again, you're writing a network game, you're writing some kind of social system that goes with it. And so I'm friends with Tony. When Tony comes online, I see Tony come online, right, in my presence. And Tony just goes to get a cup of coffee or tea. I'm not sure which you prefer, Tony, but one of those. Tea. Tony goes to get a cup of tea and he goes AFK. Now, I see when Tony goes AFK and I see how long he's been AFK, right? But it's really not much good to me if I see, Tony has been AFK for 37 minutes, 43 seconds. That's a bit too high precision. So what I want to do is show to the player, within the first few minutes, sure, 1 minute, 2 minutes, 3 minutes. But then if Tony's been gone for 44 minutes, I might say, well, he's been gone for about 40 minutes or about 45 minutes. I move to a granularity of 5 minutes at that kind of time frame, right? And so in Chrono, this is a one-liner. I can define a type, which is 5 minutes, which is the duration, 5 minutes, right? 5 times 60. And then I'll take now, and I'll take away Tony's AFK time from it, and I will duration cast that using my 5 minutes type. Now the duration cast I need because I'm deliberately losing information, right? I'm deliberately quantizing. And then notice that I am fixing the type of AFK period to minutes, right? So that line's actually doing two things. It's quantizing the type to that 5 minute quantization, but then it's assigning it back to minutes. And that's an implicit conversion because if you have something in 5 minute periods, you don't lose any information going back to minutes. And then I format it. So it's a one-liner just to do that kind of human-style quantization. Some more examples of making our own units. This is a flippant way to define a year, 525,600 minutes. An NTSC frame, 29.97 hertz, or strictly it's 30 divided by 1.001, but for this, yeah, Tony's nodding. He's an expert on these things. Or if I want to write a little helper for me to decide, how to take my medication, I might take it every 6 hours. I have one more tip really for using Extended Chrono, which is don't use high resolution clock. It sounds great. The problem is that it's underspecified. For a rule of thumb, if you want human wall time, use system clock. If you want a stopwatch, use steady clock. And if you want something truly high resolution, use a platform specific thing. In all implementations so far, high resolution clock is just a type def to either system clock or steady clock. And cross-platform, you really don't know which one. So in C++20, we got some more clocks. UTC Clock, TAI, which is International Astronomical Time, GPS, and a couple of others. And they basically work the same as system clock, at least UTC, TAI, and GPS, except with different epochs and different offsets, because TAI doesn't include leap seconds, whereas UTC does, etc. And recently I've become aware of there's a caveat around using now, because under the as-if rule, the compiler's allowed to reorder things, and there's a paper which says, what do we mean when we say now? Because that could come before or after the statement before it, depending on what the compiler does. Okay, that was the time part of the talk. Now let's talk about dates, which is by far the larger section of the talk. And the more interesting one. Up till now, that was probably mostly review for most of you. How many people use Chrono in their code bases? And oh, good. Pretty much everyone. How many people love it? About half. Okay. How many people? Okay, no, I'll stop asking. Okay. So with C++20, we got dates. Days, months, and years are all integer-like types, right? Months and weekdays, though, are enumerations, right? With wraparound arithmetic, with modulo arithmetic. Months are 1-based. Weekdays, however, are 0-based. And we got some types that just combine those things together. So year, month, day, for a date, or year, month, weekday, where you can say things like the second Thursday of April, right? And so day, month, year, they're all integral types with explicit constructors. Weekday, year, month, day, and year, month, weekday are types that represent those aggregates, right? But you can't really do arithmetic with year, month, day, and year, month, weekday. Is there a question? Yes.
Yeah. So for year, month, weekday, you actually need 4 pieces of information, right? Because you also need the
year, month.
Or,
yes.
Or
So yeah,
which,
right. So the weekday, you need 4 pieces. So the weekday is the day of the week plus which one it is in the month, right? So the second Thursday or the third Friday. Yeah, exactly. You can't directly do much arithmetic with year, month, day, and year, month, weekday. But they have conversions to sys days. And sys days is nothing more than a time point, a system clock time point, with a period of days. Anyway, here's how you create year, month, days. And I did it without using the UDLs. There are UDLs, user-defined literals, D and Y. But basically, this is probably the only defense I know of the US-style way of writing dates, which is that it's the tersest. Because if you put the month first, then the compiler knows that that type is fixed and knows the correct overload of the slash operator. Okay. So that's a brief, we went over time, we went over dates, very briefly. Now comes the fun part, the sort of non-C++ part. I need to sideline C++ for a little while because we're going to look at the history of the Western calendar, which is strange and fascinating. And there's some good mathematics to cover. And in particular, we're going to look a little bit later and talk about how to calculate the date of Easter. There'll be plenty of C++ when we get to that. But first of all, a bit of history. So the story begins in 46 BCE. Rome is not yet an empire. It's at this point a republic. And Julius Caesar has been engaging in a campaign all over Europe and North Africa. And indeed, there's been a civil war. In this wider campaign, there's been a civil war with Rome since he crossed the Rubicon and did all that kind of stuff. Anyway, he returns to Rome in 46 BCE as a conquering hero, claiming victory in these campaigns in the wider Roman Empire. And the Roman Senate, they must be fed up of civil war at that point because they take this unprecedented step of saying, yeah, you can be the boss for a long time. Like, no one's ever been we just hand you the keys to Rome for like 10 years, which they had never done before. And at this point, the Roman calendar is in a shambles. So the Republic Roman calendar was traditionally dated from AUC, stands for Ab Urbe Condita, from the founding of the city being Rome. And so it's about year 708. And like many calendars in prehistory, it was based on the moon, right, not the sun. Because if you're a farming community, if you're a fishing community, it makes more sense to go by the moon, right? Because you're the tides and the seasons. Also, it had 12 months. I mean, originally it had 10, but it had 12 for a long time by this point. They were basically alternating 29 and 31 days because the ancient Romans considered odd numbers more auspicious than even numbers. And of course, this calendar doesn't match the time it takes the Earth to go around the sun. And so it loses days every year. And every now and then you have to put in an extra month. You have to intercalate a month. And the thing is, it was actually Julius Caesar's job to do that because he was Pontifex Maximus and he'd been kind of busy running campaigns for like 4 years. So by this time, it was about 90 days adrift. This is what the calendar looked like in the Roman Republic. The year started in March. Quintilis and Sextilis were what we now call July and August. And the year ended in February. And you can see at the end there's more kind of dotted days at the end of February. They didn't have exactly a leap year day like we do. That was where they basically, when they needed it, chopped off the end of February after the 23rd and inserted this intercalary month. So yes, they had 12 months, started in March, end in February, and when required, they chop off the end of February. So after Julius Caesar was assassinated in 44 BCE, they renamed Quintilis to what we now know as July. And then later on in the reign of Augustus, Sextilis became August. Anyway, it's in the shambles. It's about 90 days adrift. So Julius Caesar, the new guy in charge, he went to the Egyptian calendar, and the Egyptian calendar was fairly normal by standards. They had 12 months of 30 days and like 5 extra days that they would just add on. I think that's actually a pretty good system that we could use today. But anyway, with the help of Sosigenes of Alexandria, they designed the Julian calendar reforms that we basically still use today. So this is basically our calendar today. They took those 5 days and they spread them, basically they spread them over the months. And then February, being the last month of the year, and having a festival there was kind of considered an unlucky month. So they kept February short. That's the reason why February is short today. Now, you might be wondering why in these diagrams I have colored days, right? Cassio knows. The reason why I have the colored days is because this is how the ancient Romans measured their dates. They didn't, and it's very difficult for us to internalize this, but like we measure the days from the beginning of the month and we just count up, and when we reach the end of the month, we go to the beginning of the next month. That wasn't how they did it at all. They had 3 important days in the month. The calends is the first of the month. The Ides is usually the 13th of the month. And the Nones is 9 days before the Ides, usually the 5th of the month. And the way they measure a date, the way they say a date, is to say how many days before the next sort of red letter day you are. And you have to count inclusively. It's very strange. Now, yeah, so you've probably heard of the Ides of March, famously when Caesar was assassinated. And that is the 15th of March. And I said that Ides were on the 13th. Well, in March, July, October, and May, the Ides were on the 15th, and the Nones were on the 7th. And so this is what it looks like to figure the date in ancient Rome. You take the day, the next red letter day that's going to occur. So here we are, we're May the 8th, so I can actually use this. Okay, so May the 8th, the next, and May happily has the Ides on the 15th, so that was actually lucky on my part. So the Ides are going to be on the 15th, so we count backwards inclusively from the 15th, and we are 8 days before the Ides of May. That's today in ancient Roman. And this is how they say it. So AD means ante diem, meaning before the day. And you count backwards. When you're the day before, you say pridie, right? Because that's just the day before. And then you go to 3 days before. Remember, they count inclusively. Okay. Leap years are even stranger. So here's the end of February in the leap year, in the Julian calendar, right? So calends of March, that's the 1st of March. That's fine. When we count backwards, you've got pridie, AD3, AD4, AD5. And then the leap day, which we now know as 29th of February, to them it was a repetition of the 23rd of February. So they said, we're 6 days before the calends of March, and now we're 6 days before the calends of March again, right? Bis. This is just some strangeness in our calendrical history. Because they counted, so Julius Caesar did the reforms, and as part of those reforms, he said, he laid out the months as we know them today, and he said, we're going to have a leap year every 4 years, right? But then he died, assassinated. And then they screwed up leap years, because he said, we'll have a leap year every 4 years. And they understood, well, we count inclusively, so that means a leap year every 3 years, right, as we would say it today. And so things were really messed up between about 44 BCE and 1 BCE or so. They had to fix things up. Anyway, all of this to say, this is very cumbersome. Stood Chrono is definitely Gregorian calendar centric. And in fact, the system of calends known as Ides persisted because the Roman Empire, arguably didn't really die out, sort of became the Holy Roman Empire and persisted until the 13th or 14th century. But this system at least persisted until the 5th or 6th century CE. And at that point, they basically said, well, we'll do forward counting now, and the leap day is going to be February 29th, and we recognize that that's all much more difficult to deal with. Okay, so with that background, let's talk about the Computus, which is the other part of the title of this talk. So if you don't know the word Computus in general in history has been used to mean calendrical calculations, how to calculate dates. And in particular, the Computus is sometimes used to mean how to calculate the date of Easter. Now, first question is why is this important? So you're an early Christian. How do you know when to celebrate Easter? You're a very early Christian in the early days of the Roman Empire. You know that you know when it should be. It basically coincides with Passover, and you probably are living near to some Jewish people if you're a very early Christian. But if you're living in the outer reaches of the Western Roman Empire, after a couple of hundred years, you need a way to figure this out. And it's not easy for the Pope to tell you because you live hundreds of miles away from Rome, right? And why is it important to know Easter? Well, you're living a hard life, right? Failed crops, famine, Goths, Vandals attacking you, Vikings. This is about your immortal soul, right? You've got to know when Easter is. This is very important. Okay, so we need to figure out when Easter is. And at this point, we have to acknowledge that the moon exists. Okay, and really, this taps into the problems that any calendar has to solve. Whether it's lunar, solar, semi-lunar. You can count suns, days, or you can count moons. And they both make sense depending on what your society does. You do really need to count days and fit things into days because all life on Earth works by the cycle of the sun pretty much. And the basic problem is, time it takes the Earth to rotate, time it takes the sun to go around the Earth to go around the sun, and the time it takes the moon to go around the Earth. They're all different and have really no relation to each other. At least no relation on a human life scale. So, in the year 325 CE, the first stab at this problem was made. And bear in mind, at this point, astronomy and astrology really mean the same thing. The first council of Nicaea, the church got together and said, we need to define Easter because there's this problem. So they said, we're Christian, we don't want to be relying on Judaism, we want to define Easter on our own. That was one thing. So they said, we're going to define the spring equinox, the vernal equinox, on March 21st, right? Even though at that point, the calendar wasn't quite in sync with where the seasons are. They said, we're going to define it on March 21st. We're going to take the first Sunday after that. And the reason I have an asterisk here is if that day is a Sunday, then you have to take the next Sunday. So this is a very characteristic thing of calendrical calculations. Oftentimes, the spec says it's the first weekday after some event, right? But you always have to take into account, what if the weekday is when that event falls? So the way to sort of properly specify that is to say it's the Sunday after the first Saturday on or after. It's slightly easier in code. After the vernal equinox, which is always March 21st. So you take the full moon after the vernal equinox, you take the Sunday after that. Okay, so how do we calculate the moon? Well, the moon has, if you Google this, you'll find the moon has basically two periods. The sidereal period, meaning the way the moon appears in the background of stars, right? And on a human lifetime, the stars are basically, you can count them as fixed. But when the moon's got to the same place in the stars, it's not the same phase, right? Because the Earth has moved on around the sun. And the moon's at the same angle to the Earth and the stars, but it's not at the same angle to the moon and the Earth. And for that reason, the synodic period, meaning the same phase period, is slightly longer at about 29.5 days. Anyway, so the early Christian church had to go at figuring out an algorithm for Easter. And the first few people to do it did varying jobs of goodness. The first guy really to do a job that really got noticed and widespread was Dionysius Exiguus, and he produced Paschal tables, Paschal meaning of Easter. He also fixed the year 1, wrongly as it turns out in hindsight. During this time there were, in the early church, as perhaps always in the church, there were schisms between Rome, Constantinople, Alexandria. Some calculations were based on one cycle, some on another. Gradually, the best minds here converged on using what's called the Motonic Cycle, which is a 19-year cycle of the moon. We'll come to that in a couple of slides. But an example of the kind of problem in history at this point, there was a king of Northumbria. England was not a country yet, so there was the kingdom of Northumbria. And King Oswy was king of Northumbria, and his queen was from Kent, which is off the map, way down in the southeast. And they each had their separate courts, right? And they each had their separate religious advisors. And there was a particular couple of years where, the queen was celebrating Easter a week apart from the king because her religious advisors calculated it according to one method and his according to another. And this was clearly a problem, like you can't both be right. And that's a danger to one or both of your immortal souls, as we said before. So they had the Synod of Whitby, and they kind of fixed which calculation method they were going to use. But this is kind of exemplary of the kind of problem that was happening. So this was 664. Well, now, in the next century, the first person comes along who really knows what things are about. And he's called Bead. He's an 8th century monk in Northumbria, which is actually, pretty much where it says Benicia there, near Lindisfarne. And he's considered the most important historian of his time. He wrote a lot. We have a lot of things from Bead. He's most famous for his ecclesiastical history of the English people. But he also wrote this amazing treatise on the reckoning of time, like how to do all these calculations. And really interestingly, he starts off actually teaching people how to do arithmetic on their fingers, which is interesting because it's kind of like this is a manual for any officer of the church to be able to calculate Easter for their parish, for their area, right? And he was really the first person really to properly understood things, although he's an 8th century monk, so he's a pious guy, right? But he's actually a scientist. He's a good observer. And he did not hesitate to call out people who had come before him who were wrong and tell them in no uncertain terms they were wrong. Like he's like, you're obviously wrong. Just look in the sky. So he produced a 532-year cycle, and that's 19 times 28. So the 19 is the Motonic cycle, the 19-year cycle of the moon. 28 is the cycle of leap years. So we've got a 7-day week. So the leap day falls on every one of the 7 days. That's 28 years. So if you have a 19 times 28 or 532-year cycle, that should be the full repetition, right? You can start again when you reach the end of that cycle. And he was the first person to notice that the Julian calendar was already slipping. Like in the 8th century, it was already, because as we know today, and as we'll see, the Gregorian calendar reforms fixed the leap years on the centuries. But it was already slipping. So, okay. This is the Motonic cycle. This is the cycle of the moon around the Earth. So 19 years, 19 solar years, corresponds to almost exactly 235 lunar months. That is synodic months, the months where the phase is correct again, right? But 12 lunar months is only 354 days, right? So each solar year, you lose about 11 days. And what you do is you accumulate those days, and like we said before, whenever you get up to 30 days, you put in an extra lunar month. And so the Motonic Cycle is a way of counting and saying wherever you are, which year you are in the Motonic Cycle, and then how many extra days or epochs that the moon has. It's basically the same way as saying how old is the moon on January 1st, right? For that year, so for the next year, right? So in year 1, we fall 11 days short. In year 2, we fall another 11 days short. So now we're 22 days short. In year 3, we fall another 11 days short, but we mod it by 30, right? So it's not 33, it now becomes 3. Now, and you do that, and you just keep a count of how many leftover days you have, always modding by 30. And after 19 years, the cycle repeats. Now, on the 19th year, you'll notice that we bump the day. There's that 30 there. That's clearly 12 days after 18. And it's just the way, because we're hammering things into integer number of days, and because the moon and the Earth don't do that, that's just the way the maths works out. Anyway, the Motonic Cycle works pretty well, and if you have these epochs, you can figure things out. There's a whole bunch of terms that go with the Motonic Cycle. Whether or not you have an extra intercalary month controls whether you're a common year or an embolismic year. Again, some lunar months, because the lunar month is 29.5 days, some are 29 and some are 30, because again, we have to hammer everything into integral days. And that extra epoch, that year 19, that extra day, that's called the leap day of the moon, if you like, as well as having like leap year days of the sun. That's the equivalent for the moon. If you look in the literature, the current year of the Motonic Cycle is usually called the golden year. Okay, so we've got a way kind of to figure out where the moon is. The other half of the calculation is figuring out what weekday it is, right? And it's a very similar sort of calculation because, again, just like 29.5 doesn't fit into 365, 7 doesn't fit into 365 evenly. So you do a very similar kind of calculation to figure out what Bead called concurrents, or we could think of as solar epochs, the equivalent thing for the sun as there was for the moon. And yeah, you accumulate them over the 28-year cycle in the same way that you accumulate the days, the epochs over the 19-year cycle. So given that, we now can sort of sketch an algorithm for calculating Easter. So firstly, we've got to figure out which year of the Motonic Cycle we're in. That's pretty much just modding the current year number by 19. And in the calculations that come up, you'll still see lots of magic numbers, like usually small integers that get added to various parts of the calculation. Those are all just to sort of line up the heavens with where we're already counting to as humans. They're not that important, but the important thing is like this thing of like modding by 19 and then figuring out the days. The multiplies and divides and mods are the important thing. The extra adding of days is just to sort of line up to where we're already counting to. They're just correction factors. So you figure out which year of the Motonic Cycle you're in. And then kind of the easiest thing to do is say, well, in some years of that cycle, I know that the Easter, the Paschal moon, is going to occur in March. And in other years, I know it's going to occur in April, and that's just sort of a small lookup table. And you may not be familiar that when I say the 14th Paschal moon, that means the 0th, if you like, is the new moon, and the next day is the first moon, and the next day is the second moon. So the 14th moon is the full moon. It's basically halfway through the cycle, right? So then you got that. Then you figure out the epochs or the concurrents the epochs for the current year, right? So then you can fix the date of that moon, and then you figure out the weekday calculation, right? The concurrents, the solar epochs, if you like, and basically you mod that by 7, and like I said, add in that fudge factor just because that's the way our numbers are now, so we're working with that. And in C++, we're back to C++ now, hooray. That looks something like this. You know, the calculations are fairly easy to write as small functions. So that, like I said, the Motonic year is just the current year mod by 19. And again, sort of ignore any fudge factors. They just make it sync up with where we're actually counting in the current year. There's our lookup table, which I happen to write as, I happen to use string.contains. EPACT, again, we've got the Motonic Cycle year, the mod by 19, multiplying by 11 because every year we get the 11 EPACTs, and then mod by 30, right? We saw that. And then the concurrence, very similar. So for every, and you're probably familiar with this, like if you think about Christmas last year, right? Christmas was a Sunday. Christmas this year, therefore, will be a Monday, right? You're probably already familiar with the fact that the days kind of move on one day each year, except in leap years when they move on 2 days. So that's what that's saying. Number of concurrence is the count of years plus the count of leap years. Again, the fudge factor, and divide by 7, or mod by 7, right? So that's the weekday calculation, basically. And we put all that together, and we say, okay, so give me the Motonic year, figure out whether it's going to fall in March or April, the moon, and then do that calculation for fixing the day of that 14th moon. And then there's the weekday adjustment to add in. And now, so we're returning the pair of the year, month, day, and the weekday. And we can't infer the weekday from the year, month, day, as you might think, because remember, we're still on the Julian calendar here, right? This is only the year 725 BCE. We're still on the Julian calendar. And that minus at the end is because the algorithm gives us a 1-based weekday and Chrono uses a 0-based weekday. That's all that is. But otherwise, this is a correct calculation. And so that gives us the date of the moon. And then Easter Sunday, we can take that date, right? That's a moon date there as a year, month, day. And we can say, well, how long till the next Sunday? And again, it's the Sunday after the next Saturday, really, that characteristic kind of calculation. Because again, if that moon falls on a Sunday, you need to count the full 7 days rather than 0. So that's that second line. And then all we need to do is do the arithmetic in Chrono. So cast that moon date to assist days, which remember is a Chrono time point with a period of days, and add on the number of days to the next Sunday. The calculation with weekdays there also comes out as assist days, right? If you take away a weekday from another weekday, the result is assist days. And this tells us that Easter Sunday this year was on the 3rd of April. Now, if you remember Easter Sunday this year, it was on the 9th of April. But remember, we're still on the Julian calendar here. And the 3rd of April in the Julian calendar is, in our modern calendar, the 16th of April. And that was indeed Easter as celebrated by the Eastern Orthodox churches. So this calculation is correct for Easter on the Julian calendar. And you know, so Bead was the first person to really get it right. And that book is about that thick and contains tons of interesting stuff. There's a few other things that Bead says. So one of the cool things here is like, when is New Year's Day? So this is kind of a mind-blowing thing to think about when you first think about it. Like if you never thought about it, like we celebrate New Year on the 1st of January, but that's sort of arbitrary, right? A popular day in history to celebrate it was actually the 25th of March. Some people celebrate it on 25th of December, or even the start of Advent, which is, I believe, is still the start of the liturgical calendar. And Bead has like an interesting explanation for this, because in his time, you know, 25th of March was popularly also considered a New Year's Day, and indeed it was New Year in England from 1155 to 1752. But Bead, you know, being a monk, he says, well, the reason for this can be found in Genesis. Now, Genesis says that, you know, God divided the dark from the light. Now we assume he divided it evenly, and so that must be the equinox, right? So the moment of creation was the equinox. But he didn't make the sun and the moon until day 4. So the first, even though dark and light existed somehow before that, on day 4 the sun and the moon were made. So the first dawn was therefore the 25th of March. So that's why that's New Year's Day, in the rationale of Bead. He also tells us some good names for the Old English months, which I include just for your edification. We're currently in the best named month, which is 3 Milky. I might be pronouncing that wrong, but it's when you milk your cows 3 times a day. And so that's why it's called 3 Milky. The other best named month is Winterfilleth, which is October, the winter full moon. Winterfilleth is, of course, if you Google it, a black metal folk band. Because of course it is. Anyway, in 1582, Pope Gregory XIII decides to reform the calendar again, right? Because by this time, the Julian calendar says a leap year every 4 years. And that gets out of sync with seasons. And by 1583, 82, 83, we're now a full 10 days adrift. So like the equinox is happening 10 days adrift from where it should happen according to the calendar. And so Pope Gregory XIII introduced this reform, which probably is well known to all of you. It's sort of a first-year computer science exercise to write a leap year calculation function. So the century years are only leap years if they're divisible by 400. And this is very expedient at the time because the first year that it really applies to is the year 1700. And if we're in 1582, that's sufficiently far away to cause no political problems. So we need a new algorithm for Easter. And this is, at first, the Lilius-Clavius algorithm. And now we see, this is another wall of text. This is characteristic of the kind of Easter algorithm you find if you look on Google, on Wikipedia. But now we can begin to decode this. They're often given in these one-letter variable names because it's just like a string of mathematical calculations where you do A, B, C, etc. But given what came before, I can help you decode this now. So A, that's a mod by 19, right? So that's calculating the moon's year, the Motonic Cycle. Pro tip, if you ever see an algorithm, you're not sure what it does, if it does mod by 19, it's almost certainly calculating either the phase of the moon or Easter. Well, then we've got a century calculation, that's clear enough. Then we've got sort of 3 quarters. Well, that's dealing with the Julian Gregorian calendar correction, right? Because every 400 years, basically, the Julian calendar has 4 leap years, and the Gregorian only has 1. That's what that correction is. There's a 3 quarters in there. And then line D, there's an 8/25ths there. Now remember I told you that the Motonic cycle, 19 years, 19 solar years, is almost exactly 235 lunar months. But only almost, of course. It's about 2 hours short, which means that in 25 centuries, you lose or gain, I forget which it is, 8 days or so. That's that 8/25ths working on B, the century. And then after that, basically we have, you can see F is doing it's doing a mod by 30. Basically in the next few lines we have a bunch of magic numbers which basically take that basic calculation and line it up with what we know to be March and April in the current year number. And this gives us Easter. And then at the end, all we need to do is, this algorithm actually produces, the base for this algorithm is March 1st. And this algorithm produces the day offset from March the 1st. So given those two things, then we can, again, a characteristic thing you see here is that we're returning a year-month day, right? We're often returning a year-month day from these things. But the sort of thing, the very last line of the function, you see the actual calculation happening in terms of sys days, because we need to calculate the stuff in cis days, and then implicitly convert that to the return type, right? So cis days has an implicit conversion to year, month, day, and that's what's happening there. Yes. So the second correction, F here, is because various reasons, but basically, a lunar month isn't exactly 30 days, and we're doing mod by 30, and also 11 days per year in terms of number of epochs. It's not exactly right either. Everything works in terms of integral days, but again, the moon does not work in terms of integral days. So that's why you see all these sort of small fix-ups. This algorithm has a cycle time of 5.7 million years. This is good. Well, I don't know if it's good for 5.7 million years, but it repeats after 5.7 million years, basically. Okay, so we're in the 1580s. We know how to calculate Easter. Great. Well, if we're in a Catholic country in the 1580s, we're good. But if we're not, so Pope Gregory says, hey, let's fix Easter. Let's fix the calendar. And, all the Catholic countries say, yes, boss. And all the Protestants and Lutherans say, hell no, we don't recognize no papal authority. And things go wrong for a few hundred years, depending on where you live and, in Europe and when you switch. And there are some very strange ideas. Like some Christians think that Easter must never coincide with Passover, which is clearly wrong. And like I say, various countries switch at various times. In Britain, I can actually say in the UK, because England and Scotland were unified in 1707, I think, the Acts of Union. It took us till the 1750s to switch, so a full 170 years after the 1580s. So the shortest year in the UK was 1751, because it started on the 25th of March, because that was New Year's Day, right? 24th of March, 1750 was followed by 25th of March, 1751. And 1751 ended on December 31st. So that year was only 282 days. And there was a few different calendar acts which brought the calendar in line with the Gregorian calendar and fixed it. But they had to do that pretty carefully, because you can't just, I can't just say that we're going to lose 10 days, which is basically what happened, 11 days. They cut 11 days out of September, I think it was, or maybe October. But you can't just say that, because, if I'm losing 11 days, I'm not paying my landlord the full month's rent, right? There's things like that happen. And likewise, the Treasury, they want to collect taxes, right? And they're not going to let me get away with paying too little tax. So all kinds of things had to get fixed up. And they wrote this law, and then they rewrote parts of it and put in extra clauses to deal with all sorts of things. Okay, and in fact, in some countries, they didn't switch till even the 20th century. So this happened in post-revolutionary Russia, was when they switched to the Gregorian calendar. And in fact, as we've seen in the calculation of Easter earlier, many countries, the Eastern Orthodox Church still calculates their liturgical dates based on the Julian calendar. But in the 20s, they did agree some reforms. They basically came to the Gregorian calendar for the purposes of sort of civil days. And interestingly, they calculate leap years slightly differently and slightly more correctly than the Gregorian calendar. So the Gregorian calendar, as you're aware, says we'll have a leap year every 400 years. So that means 2 leap years in 800 years. Well, the Eastern Orthodox calendars, they work on 2 leap years every 900 years, which actually is slightly more accurate in terms of how the Earth goes around the sun, right? That calendar is more accurate than the Gregorian one. It will, in other words, lose time less against the actual motion of the planets. But no one really bothers about it yet, because the first year it's going to diverge is the year 2800. So if you're doing calculations back in this time, it's tricky because some dates don't exist, right? As we saw, 1751 does not contain the first 3 months of the year because they just got elided. New Year's Day was moved from 25th of March to the 1st of January. Likewise, these 11 days in September were elided because of the calendar change. But not only that, not only do you have days that don't exist, you have days that exist multiple times. Because England and Scotland were the same country in 1750, had been the same country since 1707, and even before that had the same monarch since James I of England and James VI of Scotland was the monarch around 1600. And Scotland had been celebrating New Year's Day since January 1st. But England didn't celebrate New Year's Day since 1600. New Year's Day, January 1st in Scotland. But that didn't become New Year's Day in England until 1752. So in between 1600 and 1750, the same day is a different date depending on whether you're looking in historical documents in England and Scotland. And sometimes, it's difficult. Sometimes it says both, sometimes it says only one. Even though they're the same country, different sort of calendar used in two different places in the same country. So if you ever have to deal with that, good luck is all I have to say. Chrono doesn't deal with that. There is, even today, remnants of this live on. If you ever have to file taxes in the UK tax year begins on the 6th of April, right? And that's because New Year's Day used to be 25th of March, right? And like I said before, the Treasury didn't want to move the new year because it didn't want to have to deal with people paying too little tax or whatever. So they kept it, right? But with the Gregorian calendar switch, they had to advance it by those 11 days to the 5th of April. And then the year 1800 rolls around, and that's a leap year in the Julian calendar, but not in the Gregorian calendar. So it slips another day. And they fixed it on the 6th of April. They didn't do the same in 1900, even though it slipped again. But ever since then, it's been the 6th of April. That's the first day of the tax year in the UK, even today. Okay. So we've seen so far the Lilius-Clavius algorithm. Over the next couple of hundred years, we get improvements on the algorithm. And of course, it's a math problem in the 18th century, so Gauss has a go. But this kind of tells you how hard Easter is to calculate, because Gauss published one version and then amended it, and then amended it again and again, and it still has this nasty edge case. So this is Gauss's algorithm, which you'll find on Wikipedia. And again, we can sort of see what it's doing now that we know all these facts about how the sun and the moon and the earth work. First year is a Motonic cycle, then we've got, leap years and weekdays type things. We've got a century in there. P, we've got that 8/25. That's the Motonic cycle correction because it's not quite, 8 days and 25 centuries. We've got a mod by 30 and another mod by 7. So you can sort of see, you can decode this algorithm now that you know this stuff. But even Gauss, didn't get a really good algorithm. It has this nasty edge case at the end. Like, it doesn't quite come out right in this situation. So you have to do a special case for where the calculation comes out that way, and then it's actually a week off. But it's the same sort of thing. And again, you can see the same sort of thing at the bottom. Gauss's algorithm, it starts on March 22nd, right? March 22nd, remember, that's the earliest day that Easter can be, right? Because March 21st is the equinox. We have to have the full moon on or after the equinox, and then the Sunday strictly after that. Right, so March 22nd, Sunday, March 22nd, would be the earliest possible date for Easter. So that's where Gauss's algorithm takes its base. Otherwise, it's the same as we saw before. It's a little easier in the calculations. And we've got this characteristic calculating in terms of cis days, but then returning year, month, day, that implicit conversion. This is very characteristic of day calculations. Okay. So now we come to the algorithm you should actually use, now that we can understand it. This was originally published, or the algorithm that I recommend you should actually use. Let's see. Sorry, I'm hitting the mic a bit. Originally published in the late 19th century in Nature from an unknown correspondent. Most recent publication I'm aware of is in the book Astronomical Algorithms, which I do recommend. But you can find it online in New Scientist. A whole load of back issues of New Scientist are available in Google Books. You can look up that date. It's not a bad algorithm. I mean, it is, as we've seen all the Easter algorithms so far, they are just walls of magic numbers for the most part. But at least we can understand it, right? Again, we've got the Motonic Cycle. And I use std_div here because why not? But as was pointed out in the meeting this morning, std_div doesn't actually define which way around, like B and C there and D and E. One of those is the quotient and one is the remainder, and the standard doesn't tell you which one. But on the implementation I used, this worked. So just be aware of that with std_div. But I used it really to make this slide a little bit shorter, I suppose. And we've got all the usual suspects here. The Motonic Cycle is A, divide by mod by 19. G is the Motonic Cycle correction. We've got mod by 30s. We've clearly got B and C are doing the centuries, and likewise D and E, the leap years. And we've got, magic numbers after that. And it's sort of characteristic of Easter calculations that they're full of magic numbers, unfortunately. In particular, 433. I'm not sure where that came from, but that's undoubtedly some roll-up of calculations that just got sort of compacted. And the great thing about this algorithm is that basically you've got 10 lines of code, which, again, you are not expected to understand, but hopefully after this talk you understand some of. And it gives you the date directly, right? So you don't have to do any, you just say N is the month, P is the day, and the year is whatever you passed in. Okay, and if for some reason you need to calculate Orthodox Easter, there's a very similar algorithm which I won't show. Okay, so let's talk a little bit about unit testing for Easter. So I said that the earliest date that Easter can ever occur in the Gregorian calendar is the 22nd of March. That's pretty rare that it occurs that early. Won't occur that way until 2285. There have been a few early Easters in our lifetime. There'll be 25th of March, 2035 is one. And likewise, the latest it can occur is if the full moon happens right before the equinox, right, 20th of March. 21st is defined as the equinox, remember. Even though the equinox astronomically can vary a little and fall on whatever day astronomically. Remember, it's defined as the 21st of March by the church. And so you have to wait a whole lunar month for the next full moon, and then the Sunday after that. And that takes you out to 25th of April, which will occur in 2038. And this year, as we know, it was on the 9th of April, which is about in the middle of where it can be. So if you're writing unit tests, you definitely want to include these kind of edge cases. Okay. Now, one thing which might complicate things, but hasn't so far, is that in the UK in 1928, they passed a law, which was called the Easter Act. And that said, we're going to put Easter on the Sunday after the second Saturday of April. And that code would be trivial. In fact, even more trivial in Chrono if we wanted to calculate that. So we would just say, the second Saturday of April, this is the year, month, weekday use case, right? So April, there's the second Saturday, and the weekday syntax allows us to put the weekday and then index it. And then we'll take the Sunday after that, so I'm doing the plus there on the sys days, right? And this is, as far as I can tell, this is the law currently in the UK, except that it was passed by Parliament but never brought into force, whatever that means. It pretty much just means the church never recognized it, and they're the people who decide when Easter is. So, it's probably a good thing, because if the UK was following this system, it would complicate matters even further. Now, in going through all of this, at this point, a thought occurred to me. I thought, well, Chrono can do all these things, so why don't I try a direct calculation? All I need to know is when a full moon occurred, and I know that, I can look up the first full moon of 2000 was January 21st at 4:48 a.m. UTC, right? So all I need to know is a time point when a full moon occurred. And then I need to know how long is a lunar month? And that's 2.5 million seconds or so, right? That I can also fix, at least good enough for my purposes. And given those two pieces of information, I can do a very easy calculation in Chrono to figure out the current age of the moon, right? So I can just write a couple of lines. March the 21st, well, I know when that is, funnily enough. All I need to do is take away the time point of that first full moon from March 21st this year and mod that by the lunar month. And that will tell me the age of the moon on March 21st this year. Okay? Fine, great, I can do that. Given that, it's a skip and a jump to calculate the Easter moon, which is the full moon after March 21st, remember? So I can say, what's the age of the moon on March 21st? And then basically, what's the time until the next, what's a synodic month minus that age, right? So the time till the next rollover of the month. And since I'm calculating the month from full moon to full moon, that will work. Normally, when you look in the literature, the age of the moon is measured from the new moon. But in this case, I'm just offsetting the month into the full moon, right? So that's easy. So this tells me when the full moon is this year. And given that, again, a very easy calculation for Easter Sunday. All I need to do is say, give me the cis days, right? And then give me turn that into a year, month, weekday and take the weekday, right? Because I can convert between year, month, day and cis days and back to year, month, weekday. That's all sort of one-liners in Chrono. So this tells me when Easter is this year. And this is great when it works. The problem is, like, you write this code and you're like, yes, it works. You write a unit test and it's like, 2000, yes. 2001, yes. 2021, 2022, 2023, 2024, it all works. 2025, it's off. It breaks. Then the problem is, of course, that while this method is great, and as scientists and astronomers, we can say, yes, this is correct. Fact is, that's not how Easter is calculated. That's not what the church does. And so, again, when you miss by at least a week, right? Because it has to be a Sunday, and you might miss by a whole lunar month. So that's kind of unfortunate. It was a good idea, but it didn't quite work out. So, yes, calendars in general are messy human things that we try to take the motion of the heavens and hammer them into days. Even when we try to match astronomy, it's always an approximation. And on a long enough time scale, astronomy is changing as well. Like the Earth doesn't spin the same. The moon doesn't go around the Earth in the same time quite. But Chrono has lots of sort of ergonomic and easy ways to do these calculations given the right bases. So let me show you a few more examples of date calculations in Chrono. Just sort of easy one or two liners that might actually be useful because you probably don't need to calculate Easter. As entertaining as I hope it is to learn all this history, and as much as I've geeked out on it and gone down the rabbit hole this past year, it might be more useful to you to know just a few short sort of one or two liners that might come up in your code. So calculating what day of the week a certain date is very easy because Chrono lets us convert to cis days, right? So we take the year, month, day, we turn it into cis days, and then we turn that into year, month, weekday, and read out the weekday. It's a one-liner. Similarly, we can say, when is Thanksgiving? And of course, Thanksgiving is the second Monday in October, which we can do with year, month, weekday, indexed weekday this time, Monday 2. Convert that to cis days, convert that to year, month, days again, implicitly on return. Of course, if you're in that other country, it's the fourth Thursday in November. Tony's asleep, but that was for him.
I'm still.
Okay. You can calculate things like, if I have an operation on this date, and my doctor gives me so many painkillers, and I take them every 6 hours, when am I going to run out and need a prescription refill? This is an example of a real-world calculation you might have to do, that I've had to do recently. And so here we say I've got a medication period. I'm defining that type. That's a duration that lasts 6 hours. There's my surgery date. I've got 30 pills. I can calculate when I will take my last pill. And that's, again, a sys days calculation, right? So I'm saying, give me the time point that was my surgery date, and give me the medication period corresponding to 30 pills. And then that actually will be, so why is this last time point cast needed? Because that duration is a lesser period, a higher precision than days, right? So I'm losing information deliberately. I want a day back, because I just want to know what day should I go to the pharmacy. That's that. Now, I originally gave this talk at my local meetup, which for historical reasons is called the North Denver Metro Area C++ meetup. In fact, there are no other C++ meetups that I know of within like 3 or 4 states. But anyway, we have the North Denver Metro Area. So putatively, there are mortal enemies, the South Denver Metro Area, and we meet on the first Thursday, they meet on the last Thursday of the month. And this is a special use case for weekday indexed, right? So you can say first Thursday, second Thursday. You can also say last Thursday. And that's just a special use case if you need that use case, right? You need the last weekday of the month. That's available. And again, cast the sys days, return a year, month, day. And you can say, if you're doing liturgical calculations, you can say things like, when does Advent start this year? And this is I want to put this in because, again, I want to highlight, you need to be a little careful here, right? So the definition of Advent is the 4th Sunday before Easter, right? Before Christmas, thank you, before Christmas. 4th Sunday before Christmas. But that's not quite a full spec if you want to implement it, right? Because you always have to ask the question, well, what if Christmas is a Sunday, as indeed it just was in 2022? And in that case, again, you need to go back the full 4 weeks, right? And if you do this without thinking about that, one of your calculations might come out as, well, a 0, and then you'll be like a week off. Anyway, so I could have put December 24th, obviously for Christmas Eve, but sort of to make it suit the more general case, I decided to just show you that sys days cast and then take the day before. And then we're going to calculate the Sunday before that. And that's where it might actually be a 0 because, that might be a Sunday, right? And then we're going to take the full 3 weeks before that. So again, weekday minus weekday gives us a duration of days, right? Which we then take away from Christmas Eve, and then we go back 3 weeks from that Sunday. And sort of the final toy calculation I have here is like, how many Friday the 13th are there in 2023? Now you may know the answer. The answer is 2. We had one in January, we'll have another in October. And this is how I wrote it. And now I tried to write it better than this, and maybe Barry can help me out here. The problem is, I wanted to write an iota view that worked directly in months, right? Because you can increment months, right? And there are 2 problems with that. One is that months have modular arithmetic, so the point where I stop would be also the point where I started. So that's a problem sort of unrelated. That's why I have 1 and 13 rather than 1 and 12, right? Because it's the past the end iterator sort of thing. But the other thing is that iota view has a stronger requirement than months fulfill, even though you can actually pass months to std iota, the algorithm, the non-ranges algorithm, and it works fine. But you can't put them in an iota view because the concept they need to fulfill, they do not fulfill, because I believe that concept is a bit too strong. That concept, I think, is for bounded iota views. And if you want, conceptually, I want an infinite iota view and like take 12. That would have been fine, except that I couldn't write it that way because the concept wouldn't let me. But anyway, what I do here is I take an iota view from 1 to 12 inclusive, and then I convert that to a 13th of the month, and I ask, was that weekday a Friday? And then I do a count if over that. So that just in a few lines of code tells you how many Friday the 13th there are in the year. There's one more thing I need to mention. Year, month, day doesn't let you do arithmetic in general, sort of in the sense of adding days and figuring out where they are. But you can add things to it in a piecewise fashion. You can add days to the day part, months to the month part, etc. And if you add months to it, you can end up with strange nonsense dates. Like if you take January 30th and add a month to it, you get February 30th, which isn't a well-formed date, right? At least asterisk on that, but most years that is not a well-formed date. And for that reason, Chrono gives you this predicate you can call to say, is it okay? Now, so why doesn't Chrono just make it okay? Well, the reason is that there are different use cases you might want, right? There are, in particular, two common things you might want to fix up. You might want to say, well, let's just take those extra days and roll them into March. And if you want to do that, you can do that by casting to sys days and back again. Fine. Or you might want to be tracking the end day of the month, right? And in that case, you can do that just by snapping it to the month you want. To the last day of the month, right? The same situation we saw before with the last weekday of the month. You can use last in that case to say the last day of the month. So that's why Chrono doesn't automatically kind of fix it up for you. You get basically there are two common ways that you might want to do it. So February the 30th, yes, February the 30th is a nonsense date, except in the 1700s in Sweden, because it's one of these Gregorian calendar switch things. So in 1699, the Swedish government decided to change to the Gregorian calendar. And they said, well, I know what we'll do. We'll skip leap years so that we'll gradually get back in line, and by 1740, we'll be on the Gregorian calendar. Never mind that we just screwed up for 40 years, but anyway, that's how they decided it. The problem is that they decided to do this, and then they got in a big war because their neighbors were all ganging up on the relatively young king of Sweden at the time. So in 1712, they needed to back out of that decision, and the way they did it was by having 30 days in February that year. So if you're in Sweden in February 1712, you have 30 days. And then later on, they did it in one go like everyone else. Okay, so here's a plotted summary of like how to use the Chrono dates. So year, month, day gives you your standard date format, your default representation. That's a proleptic Gregorian calendar. Proleptic means just it goes back in time as if it were always the Gregorian calendar. Casting to sys days for arithmetic, you saw that in almost every code slide here. Weekdays and months will give you modular arithmetic, 7 and 12, obviously. And then, the year, month, weekday and the last variance can be occasionally important. And again, be really careful when the spec says, the nth weekday after or the nth weekday before some event. Make sure your tests include what happens when it falls on that event. Okay, that is nearly the end. If you're interested in references, I have tons of them. I've been down this rabbit hole for a year. The reason I'm giving this talk in the first place is that my wife said, you better turn all that geekery into something you can do. Right? She's like, you haven't spent all this time doing this not to come up with a talk on it. Oh, and there's this great So that's some of the books. There's this other book which I discovered. It's called The Handy Book of Rules and Tables for Verifying Dates with the Christian Era. It's from like the late 1800s. Those references are distilled somewhat into an Amazon list and a YouTube list. You can find the algorithm you should use for Easter in the Puzzles and Paradoxes column of New Scientist, 30th of March 1961, which you can find on the Google book search. And there's tons of stuff you can look at online. My final thought is that if you're a fan of Duran Duran, you can accurately sing New Moon on Monday in the following weeks of this year. And other years are left as an exercise. Thank you very much. Yes?
So, given that months and years aren't necessarily the same thing depending on, like you define months to be different things and years to be different things, do you see a valid usage of stood chrono months and stood chrono years, like the duration aliases?
The duration aliases.
Like specifically those two.
I suspect, months it is hard to see a use case for the duration, it's true, because even in our everyday calendar, months vary so much. So sometimes they get used the Treasury uses them, right? I can give you an example. The Treasury normalizes like a month to be 30 days. And I think, is that what?
No, it's not 30 days though. I can't remember what it is, but
It's like a mean month.
yeah.
A mean month, yeah.
And
So,
same with the year too.
so I'm not sure this is how Chrono, I'm not exactly sure if Chrono's definition matches like the Treasury definition, but there is a use case sometimes for the idea of a mean month when you want to calculate tax rate tables and things like that and produce the mean or over the year spread out some kind of. So yeah, there are use cases. I don't know off the top of my head if the way those things are actually done by your actual country's treasury match what Chrono defines as a month. Years probably have more of a use case than months because they tend to be. Yeah, I think the Chrono normalizes a year to 365.25 days, I think.
245.
Is it 2425? Okay, yeah. Okay, yeah. Thank you. That's actually closer. Which matches what the Gregorian calendar says. Yes, exactly. Yeah, Cassio.
So just a few comments here. So, piece of advice: don't look at those references, otherwise you get addicted to that. But it was really pleasant yesterday. So that's my first time hearing this conference, and I met Deane for the first time yesterday, and I found another calendar geek. And then, but the first person I thought was Joe, and was a third one, so I'm paradise here. So, and that's the first comment. The second one, even though we met yesterday, I mean, just look at your presentation, it feels like we agreed what each one of us would say. Because it's, of course, there is a small overlap. I cannot even say the word calendar, right? So there is a small overlap. But it looks like we agreed which.
Yeah, Cassio's talk and my talk are complementary.
Yeah, and so, for instance, and I some things that I cut from my presentation because I don't have enough time. So I'm not explaining the Camoons, the heights, the north, the area. Oh, I cannot talk about the UK tax year, that's here. So it was really pleasant to see that. Complementary to mine.
Nice.
And the Albert's point of view as well. So he covered Easter. I don't talk about Easter at all, but when he mentions that year month dates that you can convert to 6 days, and that's what I talk about. So how to, I mean, it's not something that we should do. We should just use the library, but I implement that in the library. So I explain what the algorithm does for this conversion. So it was really great talk. Thank you.
Nice.
So it kind of seems like the real problem here with all this complexity is that all these celestial events don't actually line up to integers.
Right.
So what if we just like fix the moon, right? Like we just
Yeah.
Put little rockets
Good
in
idea.
there.
Oh, they did that for the equinox, right? They said
Yeah.
21st of
Yeah. 21st of March. That's your equinox
whatever
right
the
there.
astronomers say.
I like the ancient Egyptian calendar. I like 30 days in a month and then 5 or 6 floating days, just like the holiday at the end of the year. I think that's a great idea, but that's just me.
There's been the same proposal for 13 months, 4 weeks each,
Right.
and then you get like a couple of slosh days at the end, and it's just like you were partying for New Year's anyhow.
The war night.
Right.
I missed one slide, just one slide.
Which one?
The one that you said was a joke.
Oh,
I feel so bad.
I put that in for you.
Yeah.
The it's not too far back actually. It's the Thanksgiving calculation.
Oh, the Canadian
For
one.
the Canadian.
Thank you. Got it. Yeah.
All right. Yeah.
Do you know of any like calendar libraries which like integrate like the standard Chrono library, but like provide calendars for specific like nations or that kind of thing?
I don't know specifically about calendars. I had to kind of cut off my research at some point, so I haven't done a lot of diving into all the other calendar, like Eastern calendars and lunar like the Islamic and Jewish calendars
I mean, even for the U.S., there's like multiple different stock exchange calendar. Holiday, federal holiday names like state calendar.
The answer is sadly I can't give you chapter and verse on that. Yeah.
One issue that I've run into several times with running the website is daylight savings time in America versus daylight savings time in Europe.
Oh yeah.
Do you have any recommendations for that?
Gosh. Well, the Tom Scott talk that I had on the slide near the beginning is 10 minutes of like going through. He covers that and like all the pain and there's not a good recommendation other than you have to deal with it. If you can find something open source, great.
Chrono does have time zone things in it, right?
Chrono has the time zone database. Chrono has some stuff to help with that. Again, it's part of the talk. I didn't have time. Chrono also does leap seconds. Some of those clocks, like UTC, includes leap seconds. TAI does not. Right? Currently 37 seconds adrift because of that. But Chrono has both of those clocks, and Chrono has some leap second stuff in as well. Yeah.
I have a question about the implicit conversions. Do you know why that was decided? Because it seems like it can lead to a lot of cases where you can overflow without seeing it. Like if I understood Chrono years of 300, and then or 300 years past 2,300, and then I pass it to a function that accepts stood Chrono nanoseconds, that's going to overflow.
Yeah, it is. The spec says basically under the hood you can think of the time points and durations as using int 64s. And 292 years is I think when you chose 300, right? The spec says like it's plus or minus 292 years in nanoseconds. Fits into a 64-bit integer. But yeah, if you try and convert 300 years to nanoseconds, yes, that's a problem. I haven't tried to do that. All right, I think we're about at time, so we better wrap up. But I'll be happy to talk to you afterwards.